Chapter 9, Section 1, Radical Expressions. Let's get started with a little bit of terminology. We say 5 is a square root of 25 because when you square 5, you get 25. Now, 5 is not the only square root of 25. There is another real number whose square gives you 25, namely negative 5. So then we see that negative 5 is also a square root of 25. So 25 has two square roots. Let's talk about another number. How about 36? Can you name the square roots of 36? So 36 has two square roots as well. 6 and negative 6 are square roots of 36 because 6 squared is 36 and negative 6 squared is also 36. So what we're noticing is that positive numbers have two square roots. Like, for example, what are the square roots of 100? 10 and negative 10. That's right. So every positive number has two square roots. One of them is a positive square root, and the other is a negative square root. This notation here is read as the square root of 36. Not a square root, but the square root, meaning there's only one square root of 36. How can that be? We just finished saying that 36 has two square roots, positive 6 and negative 6, right? So then which one of those is the right answer? Well, this notation here means you want the principal or the positive square root of 36. You want to find the positive real number such that when you square it, you get 36. In this example here, 36, the expression that's underneath the radical is called the radicand. And this symbol here is the radical. So you got the radical, the radicand. Whatever is underneath the radical is called the radicand, okay? So what this is really saying then is give the principal or the positive square root of 36. So therefore, the one and only answer for this is positive 6. So we would not say that this is equal to negative 6. Now this might be confusing for some people because we all know that, negative 6 squared is 36. So some people may think, well, no, negative 6 is a square root. You're right, it is a square root, excuse me, but it's not the principal square root. It's not the positive square root. 6 is the principal or positive square root of 36. We're ready to jump into some examples here. The first one says to evaluate. Evaluate means to find the value of something. So here we have the principal square root of 121. That is to say, find the number, the positive real number, such that when you square it, you get 121. The answer here is 11, correct? The answer is 11. If you want me to prove it, I would be happy to. The answer is 11 because when I square 11, I get 11 times 11, which is 121. So 11 is the principal square root for 121. The next one here is negative square root of 25. I would like to invite you to read this as the opposite of the principal square root of 25. The opposite of the positive square root of 25. Now, we just mentioned a little while ago that the positive square root of 25 is 5. However, this problem is asking for the opposite of 5. The opposite of 5 is negative 5. So this is our answer here. What we want to make sure we do not do is we never distribute a negative inside the radical. So make sure you don't do that. If you wanted for me to justify my answer here, negative 5 is the opposite of the principal square root of 25 because we know the principal square root of 25 is 5. When you square that, you definitely get 25. So the opposite of that number is definitely negative 5. The next one says find the principal or the positive square root of 169. So you have to find the positive real number such that when you square it, you get 169 225ths. Okay, find that fraction out there such that when you square it, you get 169 over 225. Now, I know that the answer here will be 13/15. That will be the principal square root. Now, please allow me to explain to you my thought process on how I know that this is the principal square root. Well, 13 over 15, right? 13/15. When I square it, I get 13 squared over 15 squared, right? Which is 169 over 225. Okay, so when I square this fraction, when I square this number, I get my radicand. Now, I do want to say something here. This was relatively easy for me to think of, okay, what number squared gives me this fraction? Because both 169 and 225 are called perfect squares, right? And in your textbook on page 729 is toward the bottom half of the page is a list of your perfect squares all the way up to 400. So please review that list so that when you come across the numbers like 169 and 225 and 256 and 361, for example, those numbers are perfect squares, and it's important that you recognize that upon seeing them. The next one is negative, and then the principal square root of 0.36. Now, I am going to invite you to rewrite this, to rewrite it as negative, and then 0.36 is really 36 hundredths. How did I figure that out? Well, 36 terminates or ends in the hundredths place. The 3 is in the tenths place, the 6 is in the hundredths place. So 0.36 is the same thing as the fraction 36 over 100. And so now I have to just think about what positive real number has the square, right, the second power, equal to 36 hundredths. And we know that when you square 6, you get 36. And we also know that when you square 10, you get 100. So this is it. Except the problem wants the opposite of that number. So then I'm going to put the negative here on my answer. Okay? So negative 6/10 is the opposite of the principal square root of 36 hundredths. Now, if you want to write this back as a decimal, you can write it as negative 0.6. The next one says this principal square root of negative 49. Now, notice that your radicand is negative. Find me the positive number such that when you square it, you get negative 49. Now, we have an issue here, don't we? Because if you have a positive number, right? A positive number, and you square it, what do you get? You get a positive number, right? And so this problem is asking you, find me the positive number such that when you square it, you get negative 49. Wait a minute, that's impossible, because whenever you square something, you will get something positive. So it's impossible to find a positive square root, a positive real number square root for negative 49, because once again, when I square it, it's going to become a positive answer. So it's impossible to get negative 49 when we're talking about real numbers. So we're going to say this is not a real number. Not a real number. That's your answer. This is not a real number. Now, later on in our course, we will have a solution for this. It'll be an imaginary number, right? Or a complex number, we can say. but we're just not there yet. Right now, we're only limiting our conversation to real numbers only. So this is not a real number. So whenever you're talking about square roots, this is very important. Whenever you're talking about square roots, the radicand must be positive. Now let's talk about cube roots. We say 2 is the cube root of 8 because 2 cubed is equal to 8. Now notice I put the cube root, and that is because it's the only real number where this is true. You cannot find another real number such that when you cube it, you get 8. And, some of you may be thinking, no, -2 is also the cube root of 8. It's not, because -2 cubed gives you -8. So really, -2 is the cube root of -8, right? So all real numbers have only one cube root, right? So we noticed earlier that every positive number has 2 square roots. But when it comes to cube roots, all real numbers only have one cube root. All right? All right, let's jump into an example here. All right, let me take you to example 6. It says, simplify this following expression. This is read as the cube root of 64. All right, a little bit more terminology here, folks. This 3 right here, that's kind of nestled in here, is called the index. And just, and of course, this is still the radical, and 64 is the radicand. But, earlier when we had something like this, I just want to say, the index was there. It's just not written. Whenever you're talking about a square root, the index is 2. But whenever the index is 2, it's just not written. We choose to omit it, right? And just assume that it's there. So I'm going to erase that. So just know that whenever you're talking about a square root, the index is 2. It's understood to be 2. When the index is something other than 2, it must be written. So then this is asking you for the real number such that when you cube it, you get 64. So the answer here is 4. And if anyone was wondering, well, can you prove that, or how is it 4? Well, I'll show you now. Here's my justification. 4 cubed, which of course we all know is 4 times 4 times 4. If you work that out, simplify this, it gives you 64. Okay? This is asking you for the fraction or the real number such that when you cube it, you get 8/27. And so this one's going to be 2/3. And the reason why 2/3 is the cube root of 8/27 is because if you take 2/3 and you cube it, you will get 2 cubed over 3 cubed, which is 8/27. All right? Now here is a perfect spot to put a plug in for page 735. Page 735 is right in the middle of that page. There's a list of perfect cubes up to 1,000. So it might be really, really, really good for you to review that list of perfect cubes on page 735. All right, the cube root of -216a cubed. All right, now the answer here will be -6a. Now let me show you how to get that answer, okay? First of all, if you have a cube root and your radicand is negative, then the root will be negative, okay? Furthermore, 216 is a perfect cube. It's in that list that I just mentioned. 6 cubed gives me 216, okay? And then when I think about a cubed, a times a times a, or a cubed is a cubed, all right? So some justification here. If you take -6a and you cube it, it would mean, of course, -6a times -6a times -6a, and this will give you this radicand of negative 216a cubed, all right? The next one here is the cube root of 125 m to the sixth power n to the ninth power. So you have to think about what real number, what expression cubed gives me that radicand. Now, let me show you the answer and then I'll work backwards, all right? I know that the cube root of 125 is 5. I know that the cube root of m to the sixth is m squared. And I know that the cube root of n to the ninth is n cubed, all right? So this is the cube root. This is the answer, all right? Now let me work backwards. All right, so 125 is in that list that I mentioned earlier as one of your perfect cubes. It's 5 cubed, which is the reason why I put 5. Furthermore, as far as the cube root of m to the sixth goes, let me show you some of my thought process there. The cube root of m to the sixth is really asking you for what expression cubed will give you m to the sixth. Now, we know our properties for exponents. We know that whatever we write inside here, and whatever exponent I write right here, will be multiplied by 3 to give me 6. That means this would have to be m squared, because 2 times 3 is 6. So that's how I got m squared. As far as n cubed here, the cube root of n to the ninth, let me show you my thought process there, means something cubed gives me n to the ninth. So I know that whatever I put inside the parentheses, the power in here must multiply by 3 to give me 9. Well, that must mean it is 3 then, because 3 times 3 is 9. So therefore, the cube root of n to the ninth is n cubed, all right? Now, with all that being said, now I want to show you something else. And it's a little bit of a shortcut that I will probably speak to you more thoroughly about in a later section, in a later lesson. Watch this. What is 6 divided by 3? 6 divided by 3, watch this, is 2. 9 divided by 3. The power on the variable divided by the index. 9 divided by 3, what is it? 3. Here, it works on the previous example too. Watch this. What's 3 divided by 3? 1. And there's a power of 1 there, right? So when you are simplifying radical expressions with variables, what you can do is take the power on the variable, and I'll speak more about this in a later lesson, but for now, I'll just say you can take the power on the variable, divide it by the index, and that'll give you the power in your answer for that variable. Let's jump to example 8 here, and I have the fifth root of 1 over 32, or 1/32. Now, we talked about perfect squares. We talked about perfect cubes. You may want to review your list of just a few of your perfect fourths and your perfect fifths, all right? But just review the first few of them, all right? That's all you'll probably need for our course. Now, the fifth root of 1/32 is asking you for what real number raised to the fifth power gives you 1 over 32. Here, let me show you like this. What do you raise to the fifth power in order to get 1 over 32? That's the question. So the answer to that question is 1/2. And let me show you how I know that, all right? So watch this, everybody. Okay, let me get rid of this here. All right, 1/2 raised to the fifth power would be the following. 1 raised to the fifth power over 2 raised to the fifth power, right? So you have to raise the numerator and the denominator to the power of 5. Now, we all know that 1 to the fifth power just means 1 times 1 times 1 times 1 times 1, which is 1. And then 2 to the fifth power is 2 times 2 times 2 times 2 times 2, which is 32. Now it's a fourth root, right? So the fourth root of negative 625 is asking you for what real number do you raise to the fourth power to give you negative 625. Now I want you to think about this, everybody. Whatever number you raise to the fourth power, you're trying to get negative 625. Is that possible? No, it's not. Because no matter what you raise to an even power like 4, you will end up getting something positive, right? So it's impossible to raise something to the fourth power and get something negative. That won't work. So, just like earlier, we're going to write that this is not a real number. Okay, not a real number. We'll have something to say about this later on in chapter 9. This will also be imaginary, okay, or complex. So I want you to notice something. I'm going to write it down at the end of our notes today, at the end of our lesson. But I want you to notice that whenever the index seems to be even, right, for square roots and for fourth roots, we run into trouble whenever the radicand is negative, right? So keep that in mind. We'll write something about that toward the end of the lesson. This one says the fifth root of negative 243. Now, someone may be thinking, well, we just said that you run into trouble whenever the radicand is negative. Yeah, but that was only for even indices. This index is odd. So I think there's an answer here. Actually, the answer here is negative 3. Now, please allow me to work backwards here. I don't want to just tell you that the answer is negative 3 and then move on. I want to show you how I know that is the case. If I take negative 3 and I raise it to the fifth power, we all know that means negative 3 5 times, right? But it's repeated multiplication. Notice that you have an odd number of negatives. You have 5 negatives, so it's negative, and then 3 raised to the fifth power is 243, right? Now, I'll be really honest with you. I know a few of my perfect fifths. So as soon as I saw 243, my mind told me, oh, that's a perfect fifth, because I've taken the time to review a few of my perfect fifths. So again, I want to stress the importance of reviewing your perfect squares, perfect cubes, perfect fourths, perfect fifths, okay? Here, I want to invite you again to interpret this or read this as the opposite of the sixth root of 64. The opposite of the sixth root of 64. Now, I know some of my perfect sixths, not a lot of them, just a couple of them, and I do know that 2 raised to the sixth power gives me 64. 2 raised to the sixth power gives me 64. Therefore, the sixth root of 64 is 2. But wait a minute, they want the opposite of the sixth root of 64. So my final answer is negative 2, because negative 2 is the opposite of positive 2. All right, last example, everybody, and then we'll write down some observations about some things that we've learned. This is asking you for the fifth root of 32a to the fifth. Now, I'm not sure you remember from earlier, but we did say that the fifth root of 32 is 2, right? Again, get to know your perfect fifths. 32 is one of them, okay? And then watch this, guys, and I'll prove why this works later on in a lesson. But 5 divided by 5 is 1. So I'll have a to that first power, the power of 1. This is the answer there, okay? This is asking you for the fourth root of x to the eighth power. In other words, they're asking you, what do you raise to the fourth power in order to get x to the eighth? Can you think of that? Yeah, this would have to be x to the power of 2. That's right, because 2 times 4 gives you 8. So the answer here is just x squared. Very good. X squared is the fourth root of x to the eighth. Next one is asking you for the sixth root of 64x to the sixth power. Okay, Here, let me move the screen up a little bit for us, yeah? Here, I know, actually, we talked a little bit a few seconds ago that the sixth root of 64 is 2, right? 2 raised to the sixth power is 64. And then watch this, 6 divided by 6 is just 1. So then you just have x to the power of 1. All right, let's do one more. All right, the next one. Actually, you know what? I forgot to mention in the previous example that we're actually assuming that x here is positive, okay? We're assuming that x is positive. Why do I say that? Well, I don't know if you remember earlier of me saying that every positive real number has 2 square roots. Well, every positive real number also has 2 fourth roots. Every positive real number also has 2 sixth roots. I don't know if you remember, but in the very beginning of the lesson, we mentioned that the square roots of 25 are 5 and negative 5. The square roots of 36 are 6 and negative 6. The square roots of 100 are 10 and negative 10. So positive real numbers have 2 square roots. Likewise, they have 2 fourth roots. They have 2 sixth roots. So which root do you list? Well, so that we're all talking about the same root, we want to talk about the principal square root only. Same thing here. We want to talk about the principal sixth root. Principal meaning positive. So anyway, all that to say, we're assuming x is positive, and that's the reason. Now, for the last example, the same thing, right? We want to make sure that x plus 1 is positive, right? That is to say, we want to make sure that we're giving the positive fourth root of this expression, okay? And we can guarantee that it is as long as we assume that x is positive, all right? So let me just say that x is assumed to be positive. All right. Anyway, we are talking here the fourth root of x plus 1 to the fourth power. I'm going to write down the answer, and the answer is x plus 1. And what I would like to do is show you the justification. Now watch this. Of course, the little shortcut is 4 divided by 4 is 1. So then you just have x plus 1. But here's my justification. If I take the expression x plus 1 and I raise it to the fourth power, notice that this is just x plus 1, of course, times x plus 1. Don't worry, we're not going to have to distribute. That would be a lot of work. Times x plus 1 times x plus 1, right? 4 times. This is, of course, the same thing as x plus 1 to the fourth power. So if you take this expression, x plus 1, and if you raise it to the fourth power, you will get x plus 1 to the fourth power. Some folks would like to say this: the fourth root cancels out the fourth power. They are inverse operations or opposite operations, so that all you're left with is this base x plus 1. Okay, and yes, that's true. You can do that. All right, you guys, just a little summary before we end this lesson. If x is positive, okay, if x is positive, then we know that the nth root of x to the nth power, like this, will just give you x. Okay, everybody? And that's kind of like what I was saying just a second ago. The nth root and the nth power cancel each other out, if you will, right? Because they're opposite operations, and you're just left with x, right? The formal language here is x is the expression such that when you raise it to the nth power, you will get x to the nth power. X is the nth root of x to the n. Now, if x is negative, right? So the radicand here is going to be negative. If x is negative and n is odd, the n is your index, right? So you're taking finding an odd root, like a cube root or a fifth root or seventh root or whatever, and your x value is negative, then this is what we found, that the nth root of x, right, is a negative number. All right. So this is negative and this is odd. Then your answer, your root, your odd root is going to be a negative number. The last thing we want to say, if x is negative, that is to say, if your radicand is negative and your index is even, that's where we got into trouble in this lesson. One more time. If the radicand is negative and your index is even, then this is not a real number, right? Not a real number. And you can rewind this lesson and look for when we gave this as an answer, not a real number. You'll find that the radicand was negative and the index was even. All right, everybody, I hope you enjoyed this lesson. It was 9.1. So I will catch you in the next lesson, which will be 9.2, rational exponent. All right, see you later.